Folks, we are here looking at AB38 natural log and integration, and we're going to be doing a whole lot of U substitution. Lots of it, all over the place. So let's do that. The first thing that we want to keep in mind is, it was easy to consider that the derivative of natural log was just 1 over x dx. So then the antiderivative of 1 over x dx is natural log of x. But notice this absolute value. Why are we saying that? Well, over here, positive or negative inside this piece, okay. But over here, only positive. So how do we take something where we could have had a negative before, but now it can't be negative? Well, to force the positivity in there, we'd have natural log of x. More complex is when we see it in forms of layers with substitution. We got the 1 over u and the du here. And it's going to fit that same pattern, but pretty much all the time you won't see this simple one. It's going to be the more complex version with a u, like a chain rule, substitution, layers, etc. So let's start out with the first one. We have 4 over x. Okay, so I look at this in a couple ways. This is about as simple as it would get. I'd have 4, which is a constant, times 1 over x dx. Now that constant multiple, the same way with derivatives where it stays, it kind of stays here as well because it's times dx at least. So we'd have the 4 there. Then the antiderivative of 1 over x dx is natural log of absolute value of x plus c. Okay, that's it for that one. Not too hard, I suppose. Let's look at these others. For each of these next ones, we're going to have to deal with some type of substitution. Start. What is the substitution? Well, I see that it says 1 over u, so this right here must be my u. So if u equals 5x minus 2. So, well, let's make this substitution. Then I'd have the antiderivative of 1 over u times dx. Okay, now I need a second layer of substitution because I can't have mixed variables here. I can't have u and dx. I need to somehow get it all to be the same. So I need to take du dx. What's the derivative of u with respect to x? Well, that would just be 5. Doing some algebraic manipulation, we would get 1/5 times du is going to be our dx. So that would help me translate this even further. I'd have to have a 1/5 in here. I still have the 1 over u, that hasn't changed. But then I have my du. Okay, so there's my pieces. Now that I'm at that stage, I could have written this down here, 1/5, 1 over u du. The 1/5 is a constant, that just stays. The 1 over u du, that becomes natural log of absolute value of u plus c. Keep going. Very similar here. So again, my u is going to be this bottom term. So we would have 3 minus 6x. Let's go ahead and substitute and see what else we need to deal with after we substitute out that u. That's not a u. That's a 4. Let's make it look more like a 4. There we go. 4 over u dx. Again, u and dx not going to be okay, so we do the du dx to facilitate another substitution. The derivative of 3 minus 6x is just negative 6. I notice that I don't really have a negative 6 there, so that's not going to help me. So I'm going to do some algebraic manipulation. I'll have du, and I got a negative 1/6 equals dx. Now I can take out this dx and replace it with negative 1/6 and a du. So I'll put a negative 1/6 here. And I got 4 over u, so times 4. And then I'm going to put the 1 over u separate, times 1 over u du. Hey, look at that. That'll work for us because now we've narrowed it down to just constants and 1 over u du. So the constant in this case would be a negative 1/6 and a 4 in the numerator, so that's negative 4 over 6. You could even simplify that with the 3 on the bottom, 2 on top. So negative 2/3 times What's the antiderivative of 1 over u du? It's just natural log of absolute value of u plus c. Alright, continuing on here. Slightly more complex in the layers, but same application as what we've been doing so far. U is this bottom term, so u equals x squared minus 4. So now when I make this substitution, I'm going to have 7x and a dx and u. So I got to get rid of this x and dx and maybe the 7 too. Let's see how we can work our way around that. So I need to take the du dx, and that would give me 2x. Now the 2 doesn't really seem to help me, so let's go ahead and pull that over to the du side and move the dx over with dx. That would give me 1/2 times du equals x dx. Now I can take out this x and dx and replace it with a 1/2 in du. Notice that I'm not taking out the 7. The 7 is going to stay. So that means I'll have a 7 times 1/2, or just 7 halves, because that's the 1/2 and the 7 put together. And then we'd have 1 over u, because that u is still there, and du, because x dx is gone and replaced with du. So this time our constant is going to be 7 halves when we take the antiderivative. The antiderivative of 1 over u du is natural log absolute value of u plus c. And there we go. Let's look at the next one here. Alright, so these 4 actually are deceiving, because you look at them and you're like, oh, it looks like I got something and then its derivative on top, and then that would be a natural log. But here's kind of a clever key to look for. This is 1 over x to the first. This is 1 over u to the first. And why does it even matter that we would need that? Well, let's kind of break that down here for a second. If I were to have, 1 over x squared, like this, and take this derivative, I would probably change that first to x to the negative 2, so it's a little bit easier to do the calculation. And then I would just use a power rule, and negative 2 plus 1 is going to be my new power over negative 2 plus 1. So this is becoming x to the negative 1 over negative 1. Simplify that even further, we'd have negative 1 over x. Alright, so not too big a deal. We could do that with really over any power, like this. We could have 1 over x to the n, that becomes x to the negative n dx there. Let's not forget the dx. And then that would become, oh, of course, plus c, plus c, plus c, plus c, all the way across. And then we get x to the negative n plus 1 over negative n plus 1, and then plus c. But when we have 1 over x to the first, here's the problem. If I were to change this to x to the negative 1, and then follow this same pattern, let's put dx's in there, then I would have x to the negative 1 plus 1 over negative 1 plus 1, which is really x to the 0 over 0. That doesn't work. Doesn't work. So power rule doesn't work for n equals negative 1. Or not even negative 1. Yeah, for n equal, no, for a power of negative 1. For 1 over x to the first. So we use natural log, because it seems to fit the pattern. So let's look at these and how they're significantly different. So first thing, this radical makes it not first power, because let's say a lot of people were to look at this and they would say, oh, u is that bottom piece, so u equals 16 minus x squared. Very good. So then I'd have the antiderivative of x dx over u to the 1/2. And look at that, 1/2 power, not 1, not 2, not even 0. It's 1/2. And it would have to be a 1 in order for us to think of this as natural log. But it's not. So I just keep doing normal substitution patterns, normal substitution protocol. So if I look at du dx, that would just be negative 2x. Simplify it even more. Get rid of this negative 2, move over the dx. We got negative 1/2 du equals x dx. Now I can take out this x and this dx. Those are gone. Replaced with a negative 1/2 and a du. And this u to the 1/2 is really u to the negative 1/2. This we can do with power rule. No need for natural logs. So add 1 to the power. It becomes negative 1/2 u to the 1/2 over 1/2. We've got 1/2s everywhere, plus c, of course. And we flip, multiply, simplify. You got negative u to the 1/2, or square root of u, plus c. So no natural log there. And it's because this is not power of 1, which means there's no natural log. Okay, let's do more. This next one, right away, you should be able to start to see some consistency. This is not power of 1. So I am going to say that u equals 2x minus 1, but that's going to give me the antiderivative of 1 over u to the 1/3. We got this dx. Now again, we got to get rid of the dx and stuff, but it's u to the 1/3. It's not the power of 1. It's 1/3, which means we could just use power rule. No big deal. Okay, so what do we need? Oh, du dx. Du dx. So we take the derivative of u with respect to x here, and this is really u to the negative 1/3. Oh no, wait, no, we don't need that. Du dx is just going to be 2 of u. So we don't need the 2, but we should somehow get the dx by itself, so that would give me 1/2 du equals dx. Alright, from this point, we can make all the substitutions. We take out the dx, it's gone. Replace it with a 1/2 du and the u to the negative 1/3 in the middle. Now just take the antiderivative, simple power rule, constant stays. U to the negative 1/3, negative 1/3 plus 1 is 2/3, so u to the 2/3 over 2/3. Now if we were to kind of simplify the fractions there, you would wind up getting 3 over 4 u. Well, what is u? U is 2x minus 1, I believe. But let's double check. Yeah, 2x minus 1 to the 2/3 plus c. And that's it. Easy breezy, lemon squeezy. Okay, now we see natural log in the integrand, and we haven't seen that before. So that's kind of curious too. So I'm going to try and, considering that this is telling me it's not going to be a natural log 1 over u du kind of thing. It's not that. It's something a little bit different. Let's think of what it might be. I think it's going to have a substitution because I see some complex layers in it. And if I were to think about what to substitute, I always look to that inside layer. In this case, it's natural log of x. Well, if I were to do that, I would have the antiderivative of u to the 4th over x times dx. So I got to get rid of this x in the denominator and the dx. So let's take du dx and see what happens. Du dx, the derivative of natural log of x, is just 1 over x like that. Okay, so actually I could use that dx, or that x in the denominator. Look at this. 1 over x times dx, and that's what I have here, 1 over x times dx. So I just take those out, replace it with a du. Now it's simplified to u to the 4th du. And the antiderivative of that is u to the 5th over 5 plus c. Super easy. Super, super easy. Okay, so let's finish this out, and then we'll get into some of the applications here. So I got x squared minus 2x plus 1 over x. Looks hard, but really not. Because if this had said, let's do this in orange here. If it said x times x squared minus 2x plus 1, everybody in the room would be saying, oh, just distribute the x. And what's the difference between these two? It's really just dividing or multiplying. Okay, so I just need to multiply. So I'm going to multiply, instead of an x to the first power, it's really x to the negative first power, or divide by the x. So I can simplify this into 3 terms. So it would become x squared over x. And I'm going to use multicolors here. So x squared over x, let's do purple for the second term, minus 2x over x, and then the last one we'll do green, plus 1 over x, and dx for all 3 of these, of course. Now for the first one, that just simplifies to x to the first. Should probably do this just to make it look official. And so that's x to the first, so we can deal with that one. The second one here in purple is just going to be minus 2. And then the third one is that 1 over x dx. So we'll deal with that in a second here. Let's look at the first one. What's the antiderivative of x to the first? That's just x squared over 2. The second term is going to be minus 2x to the first over 1. And then the third term, the antiderivative of 1 over x is natural log of x, absolute value, I should say. Natural log of absolute value of x. And then, of course, we have, at the very end, plus some type of constant. So there we go. That was way easier than you would think if you were looking to split it up. Now, one thing that kind of helps here, this is particularly easy because this is a single term. And you could do that practically in your head. Now, if it's not a single term, you still can do it as long as the power in the bottom would divide into the highest power in the top using long division. We might look at more examples like that later, but for now, this single term distribution of dividing throughout, really not hard to do, but something you're going to have to remind yourself to see. Alright, let's look at this last page here to wrap this up. Trig. Oh my goodness. We see trig and we go crazy. Why? We just love it too much? Is that what it is? No. People freak out with trig, and you really shouldn't. You really, really shouldn't. So let's see first what's happening. I think it might be helpful if we were to rewrite these, at least this first one, yeah, the first, second, and the third one, in terms of sine and cosine, so we can see some numerators and denominators. So for example, this is really sine of x over cosine of x times dx. Now, I know a little bit about these in the sense that these are kind of derivatives of each other. Kind of in the sense that derivative of sine is cosine, but the derivative of cosine is negative sine. So I got two options, and let's see which one looks more favorable. Let's say u was my top term, then the derivative would be the bottom term. Can we do that? I don't think so, but let's see what the alternative to that would be. If u was cosine x, the bottom term, then this would be, we would need a negative up in the top, so we'd have a negative du up top. Can we deal with that? Yeah, we can actually. So let's work that out. If we say u equals cosine of x, then let's go ahead and work out du dx. Du dx is going to be negative sine of x. So a couple of things that we need to balance here, this negative and the dx. We'd have negative du equals sine of x dx. So I need the negative du in there. So we're going to have a negative and then 1 over u du. The negative really just translates to like a constant would, so it's just going to tag along. 1 over u du is natural log of the absolute value of u, which in this case is cosine of x, and then plus c. See, that wasn't too hard. This next one you might even think of as slightly easier and not trying to balance negatives. So I see cotangent, which is kind of the reciprocal there, tangent. So we would have cosine 3x over sine 3x. Now again, dealing with the same structure, we'd want our u to be this bottom term, and then the du can match with the top term there. So u is going to equal sine 3x. Do keep in mind that now when we do our du dx, because we're going to need that part for the substitution as well, we are going to have a chain rule here with this 3. So it's going to be sine 3x times 3. So, okay, we got the sine 3, oh, cosine 3x. What? Gotta watch the trig. This is cosine 3x times 3. I have the cosine 3x, but I don't have a 3. So I'm going to move the 3 over to the other side. That'd be 1/3 du. And we have the cosine 3x dx. Alright, now I'm ready to substitute. I got the dx, the cosine 3x, the dx, the cosine 3x. So those are out, and they're replaced with the du and a 1/3. And then I have the 1 over u. And check this out. Constant stays. 1 over u du, natural log of u, which in this case is sine 3x. Absolute value in there, of course. And then plus c. Okay, now this next one, not exactly obvious again, but just kind of keep in mind that the more complex term should be your u. It's kind of like the one that has more pieces to it, because when you take the derivative, some of those pieces go away. Also, it's more helpful to have a u in the denominator than a du in the denominator. So let's start with that idea. U equals 2 plus sine of x. So if we were to make a substitution, we'd have cosine x dx, pardon me, cosine of x dx over u. So we got to get rid of the cosine x and dx, and we know that du dx, the derivative of the u that we chose, is the 2 goes to 0, and the sine x changes to cosine x. Now we can multiply both sides, get du equals cosine x dx. Now we got the pieces that we need, cosine x and dx. Those are out, replaced with du. So I'm going to have 1 over u times du, which is super simple. It's just natural log. Absolute value of cos of u, which in this case is 2 plus sine of x. I need a little bit more space here. 2 plus sine of x plus c. Okay. The last one, the finale. Okay, there's a couple things going on here. And you might be thinking, okay, so u equals cosine squared x tangent x. You could say that. You know, that could work for you. We could simplify some things and try to work our way around that. There's a couple of things I see. So here's one. If I were to try and simplify this, cosine, just the denominator, cosine squared x times tangent x. And what would that be? Okay, that would be, well, this is sine over cosine. So one of these cosines, we get rid of that one. Then we'd have sine and cosine. And then you'd have kind of this weird, 1 over cosine times 1 over sine. But here's something that I see that would actually help us move along a lot easier. And it's trying to piece this thing together in such a way that you'd have a derivative on top and an original on bottom. And here's what we could do. If we were to say tangent x here, and then in the numerator, instead of having cosine squared in the denominator, we put secant squared x in the numerator times dx. Now look at what that does for us. If we use u for our tangent x, u equals tangent x, and we know we're going to need the du dx, so let's go ahead and work that out. Du dx is going to be secant squared x So du equals secant squared x dx. Okay, at this point, I have the pieces. I got u in a denominator and du in the numerator. So here's my u in the denominator and du in the numerator. So I'd have u down here, 1 over u times the du in the numerator. So that's just natural log, absolute value of u, which in this case is tangent, plus c. Right, now there's some advanced reasoning going on there, and it's trying to match this trig into something where you have a du over u. And what even led me to do that? Probably, I probably remember this problem from somewhere, and that's what was going on in the back of my head. But, there's seeing all this stuff here that I started with, I knew it was going to hit dead ends because I would have had like 1 over sine times 1 over cosine, and that's really saying like, cosecant times secant. You just got a big mess there, and it's hard to really see like where you would go with that. But knowing that cosine squared and tangent can be kind of like secant squared and tangent, that's probably the biggest clue. That you can manipulate cosine squared into secant squared just by using it as its reciprocal. Okay, so that's it for natural log. Plenty of practice for you guys to do. But we will see you later.